Welcome back to Module 9 of our thermodynamic video series. Following the previous video on adiabatic flame temperature, today what we are going to do is take a look at an example and apply that method that we talked about to figure out what the adiabatic flame temperature would be. So let's focus on an example that consists of us burning octane, liquid octane, at 1 atmosphere in air. Let's assume that both the air and the octane, C8H18, come in at 25 degrees Celsius. And of course that the combustion chamber where this happens is perfectly insulated, meaning adiabatic, that all the fuel is burned. In other words, there's no fuel left in the products. Okay. Specifically, let's look at the case where the system is running at steady state, where the kinetic and potential energy effects are negligible. So it's all a thermal energy component thing. And the rate of air flow into the combustion chamber with respect to the amount of fuel that's coming in is the theoretical amount of air for that amount of fuel. In other words, the reaction is stoichiometric. So all of the fuel molecules react with all of the oxygen in the air. So our goal is to find the adiabatic flame temperature in this scenario. So as usual, let's start with a little sketch of what we're talking about. The sketch is very similar to what we did last class. It's going to be a flame that's made up of octane coming down at the bottom there, and on the top of the screen where you can't see is the air coming in on side 1 and coming out as combustion products on side 2. So side 2 is going to be the combustion products at the adiabatic flame temperature. Our assumptions for this model are that we're running at steady state, that the combustion chamber CC is adiabatic, there's no shaft work of course, and that we have a stoichiometric reaction. Part of our engineering model here is the combustion of octane, which I'm highlighting here in terms of the unknown products, which are going to be water, CO2, and nitrogen, which you would see in another video. And the stoichiometric coefficient of air for per mole of fuel for a hydrocarbon is x plus y over 4, as we saw again before. So without going through the details of balancing the equation, because that's done somewhere else, presented somewhere else, you can show that the number of moles of each product, and you get this simply by balancing each element on the left-hand side with the same number of elements on the right-hand side, must be as such: 8 molecules of CO2, 9 of water, and 47 of nitrogen, all of which must be in gas phase for this particular analysis. In a higher heating value analysis to come out later, we could consider that the water is condensed. We're not going to do that here. So from equation 2, and where is equation 2? That equation 2 is from the previous video before. This is the equation that gave us the relationship between the enthalpy of the products, the change in enthalpy of the product above the reference point at which the products and the reactants are referenced in terms of enthalpy, which is 25 degrees Celsius in 1 atmosphere. The equation 2 gives us the change in enthalpy of the products compared to that reference state. So that's going to be a function of the new temperature, and the new temperature is the adiabatic flame temperature. For the reactants at the reference state, since we're at 25 degrees Celsius to begin with, the change in enthalpy for those reactants is going to be 0 necessarily, because it's the same temperature. Now, next we need to look on the let's look on the left-hand side first. For each of the products, we're going to have 8 times the change in enthalpy for the CO2, plus 9 times the change in enthalpy for the water, plus 47 times the change in enthalpy for the nitrogen, because those are the stoichiometric coefficients we've got in equation 3. On the right-hand side, all that's left is the sum of the enthalpy of formation of the reactants and the sum of the enthalpy of formation of the products. So let's look at each one of those. In case of the reactants, that's going to be the oops, I made a mistake there on the composition of air. So 3.76 moles of nitrogen per mole of oxygen. So the enthalpy of formation of the oxygen and the nitrogen is 0. Check out table 825 if you will, or the fact that it's a stable compound at reference states. That's how the reference state is defined. Arbitrarily set that point as 0. But the enthalpy of octane, CH18, is not. So again, table 825 gives us that value at the reference state, which is minus 249,910 kilojoules per kmol. In other words, it absorbs 249,000 kilojoules per kmol in order to produce CH18. All right. You can also use ease to look up these values. Also on the right hand side is the enthalpy of formation of the products. So in this case, CO2, H2O, and N2. Again, the N2 is going to be 0, but the H2O in gaseous form is not, and it has an enthalpy of formation of minus 241,820 kilojoules per kmol. Similarly, for the CO2 in gas form, the enthalpy of formation is minus 393,580 kilojoules per kmol. So that's also on the right hand side. Notice there's a minus sign though in front of that. And that gives us, once we substitute all into equation 3, sorry, equation 2 actually, that should be equation 2. We are going to find that the enthalpy, the sum of all these guys with the minus sign in front of the products, yeah, the products is going to be a positive number. Add it all up. All right. And yeah, 5,075,110 kilojoules per kmol of moles of liquid octane burned. Yeah, there's a little typo there. Should be a plus sign. Plus 5 million. Now, on the left-hand side, what we're left with for these three species, the CO2, the H2O, and the N2, at the adiabatic flame temperature, they're all a function of that adiabatic flame temperature. So as we go up from the reference state, the enthalpy, the change in enthalpy of each of these three species goes up. And we need to take that into account. We need increasing it until we finally equal that 5,075,000 kilojoules per kmol number that we got before. The way to do this is to either look at tables of enthalpies at different temperatures or using ease. And we'll look at that later as well. An alternative method for solving these types of problems, which makes the computation of the right-hand side a little bit better, a little bit easier, is to look at the lower heating value of the fuel. Lower heating value meaning that we're looking at the energy released when all of the products are in gas phase and none of the water is condensed. If you condense the water, you release more heat, and hence that would give you the higher heating value, HHV. But here, for the lower heating one, the value for octane is 44,430 kilojoules per kilogram. You're going to find that for most hydrocarbons around the 40 to 50,000 kilojoules per kilogram range. And you can get that from a bunch of tables on hydrocarbons and on fuels, on engine fuels specifically, but that's what that is. Furthermore, CH18 has a molar mass of 114.22 kilograms per kmol. So that gives us a change in enthalpy of combustion of 5,074,795 kilojoules per kmol. So wow, that's really close to what we did with our enthalpy of formation analysis up there now, isn't it? In fact, it's within, well within 1%. I think it's around 0.01% of the other method. Clearly, using the lower heating value is a simpler method for finding out the right-hand side. So I encourage you to look into that. That's a method I like to use when I do engines type work for figuring out the amount of energy released per unit of fuel burned. Okay, so now we're in good shape. Let's substitute all this back into our equation 2 to get what the sum of all these change in enthalpy, compare that to what we have on the right hand side. So the only unknown at that point will be the temperature at which we calculate these different enthalpies. Let's type all that in together. That's our equation 3 that we're rewriting again. Still carrying that darn minus sign here. I'm going to have to get rid of that pretty darn soon. Okay. It's plus 5 million on the right hand side here. And yes, so now we're going to be looking at the change in enthalpy for these three species, the CO2, the H2O, and the N2, multiplying that change in enthalpy by the stoichiometric coefficient, 8, 9, and 47 respectively. And here I've looked it up. Actually, I got it right out of the book for 2350 Kelvin and 2400 Kelvin. And that gives us these enthalpies respectively for all three different species. Next, we just add them all up according to equation 4. And in the first case, 2350, we see we get slightly too low of a value here, 4,955,163. Whereas at 2400, we're a little bit above at 5,089,337. So our 5,075,000 is somewhere in between. And interpolating between those two values, as you normally did, as in your previous thermal problems, you're getting an adiabatic flame temperature of 2395, and that's your final answer. Next, we'll look at doing that using ease to make the calculation somewhat simpler. Hope you enjoyed. Take care.